Hi students. So I'm going to use my handouts that are found on my website. And this one you can see is day 8. So this would have been part 2 of acid and base dissociation. So let's go through this together. And I'm going to use rainbow pencil again. And this is the dissociation for acetic acid when it's reacting with water, and it's going to form this anion and then the hydronium ion. So what is it acting as? Is it acting as an acid or a base? Well, this is going to be my conjugate acid, which means this is acting as a base. This is an acid, so this would be my conjugate base. But you can see that this became negative, became an anion, so it's acting as a base. It's acting as an acid. It's giving away a proton. Because it's acting as an acid, we're going to do Ka equals, okay, and it's just my aqueous entities that are dissociating, right? So for this, I am going to have to look at the concentration of acetic acid when it is still molecular, when it still hasn't dissociated, okay? And so when we're solving equilibrium problems that involve acids and bases, let's go through the steps. You obviously write the chemical equation because we have to look at stoichiometric relationships between all the different entities, whether it's a 1-to-1, 2-to-1, whatever, okay? Enter any values. You guys know about ice tables. Then let X represent the change in concentration. For problems that give the initial concentration of the acid, so the concentration of the acids, compare the initial concentration of the acid with the acid dissociation constant, Ka. We're going to do the 500 rule to simplify things, to see if we can make it easier for us. And then we can make the X negligible, the change in concentration from the original concentration of acids to the dissociated amount of acid, or you're still solving X for the hydronium ion that's produced. And the reason why, again, we're able to use the 500 rule is because we're dealing with weak acids, weak bases. They're going to be experiencing dissociations that aren't really going to change the concentrations of the initial acid or base because of the low dissociation amount, okay, and because of significant digits. So if you have 0.1 and the concentration of the hydronium ion is 0.00001, it's negligible. Okay, so propanoic acid is a weak monoprotic acid, so monoprotic. So which hydrogen is it going to remove? So CH3, no, it's not going to remove any of these ones. CH2, no. It's going to remove this one here. This OH, this hydroxyl group, is going to lose that hydrogen there. It inhibits mold formation in bread. A student prepared a 0.1 molar solution and found that the pH was 2.6. What is the acid dissociation constant for the propanoic acid? What percent of its molecules were dissociated in the solution? So this first part, what's the acid dissociation? So it's asking what's Ka equal to? And then this is going to be the percent dissociation. So we're going to take the concentration of H3O plus over the concentration of the acid, the original acid, HA, times 100%. So those are the two things that we're going to do. I'm sorry I'm so sniffly. I am honestly either getting sick or getting allergies. All right. So how are we going? I don't feel like writing out propanoic acid, so I'm going to go HA. This is just for acid, my generalization, plus H2O liquid dissociates to form the conjugate base, so the negative anion plus hydronium ion. Okay, so what information do we have? Well, we can fill in this part here, 0.10, and nothing's going to happen for water. These two are going to be both zeros as well, okay? Now, there was a piece of information that was given to us. The pH is 2.96. So that means my concentration of hydronium ions is going to be 10 to the power of negative 2.96. Just do that on your calculator. Oops, it's 1.1 times 10 to the minus 3 molar. So when I'm looking at this, and I know it's going to be minus x and plus x here, this is actually equal to the x value. Okay, 1.10 times 10 to the minus 3. Okay, which means I can calculate here 0.10 minus 1.10 times 10 to the minus 3. And I get 9.98 times 10 to the minus 2. Okay, the only reason why I was able to do that was because the pH was given to me. Okay, so it's asking us now for the Ka. So the Ka is the concentration of the conjugate base and the hydronium ions, and the initial concentration of propanoic acid. Or sorry, not the initial, the final concentration of propanoic acid. So when I put all this together, I'm going to simplify it because both of these concentrations are the same. So it's 1.10 times 10 to the minus 3 squared over 9.89 times 10 to the minus 2. And so I get a Ka value of 1.22 times 10 to the minus 5. And again, it's unitless. So I'm just going to leave it like that. And then for my percent dissociation, I'm going to take now my final concentration of hydronium ions. Really, it's either or. I guess in this case, it would be the conjugate base over the initial concentration of propanoic acid times 100%. So we're using the initial, we're not using the final, because we want to say out of the total amount of propanoic acid, how much of it actually dissociated. So we're going to put 1.10 times 10 to the minus 3 divided by its original concentration, which is not 0.1, it's 0.10 times 100%, and we get 1.1% dissociation, which falls well in the weak acid range, nowhere near the 99.9%, the almost 100% dissociation. Okay. Let's look at this one here now. Formic acid is present in the sting of certain ants. I don't know if you've ever had a bite from a bullet ant. I hope not. I was thinking of fire ants, actually. Fire ants or red ants, especially in the tropics or in southern United States. We do have them in Ontario, but they inject you with formic acid and you get like a little blister. It's asking, what is the pH of a 0.025 molar solution of formic acid? And they give you the Ka. Okay, so this is one of those questions where it looks like you don't have a lot, but you actually have everything that you need to answer this question. So let's first start by creating our ice table. So which hydrogen is going to come off? It's the one here beside the oxygen, the hydroxyl. It's going to make more sense when we go into organic, or if you have your your biology credit already. So I have an initial concentration of 0.025, and I have nothing of the dissociated species. I'm getting rid of the water, and I know that this is going to be minus X, and this is going to be plus X. Oops. Okay, and we're going to leave it like that. Let's check, however. Let's do the 500 rule. So what we're going to do is we're going to do 0.025 divided by Ka. So 1.8 times 10 to the minus 4, and guess what? We get 138. So this is not negligible. We have to do quadratic. So over here, I'm going to set up my equilibrium. Expression for the dissociation. Oh, and I just messed you guys up because I put this hydrogen here. It doesn't matter which hydrogen you take off. Okay. All right. So then we're going to plug in everything. So now I have my Ka. I know that it's 1.8 times, 1.8 times 10 to the minus 4 equals X squared over 0.025 minus X. Oh, we have to do quadratic. Okay, so you can pause the video, try sorting it out yourself. I'm just going to show all my steps and be quiet while I do it. Okay, so hopefully you get to this point. You're going to find that you get two roots. And let's think about it. So I always say that there's a real root and like a mathematically possible, but realistically impossible root. Can you have an X value of a negative number? No, there's no such thing as a negative concentration. So therefore, the only real the only real number is 0.0020. Okay? So when I come over here, X equals 0.020 mole per liter, which means that the pH is negative log of this concentration, and I get a pH of 2.70. So that's why it burns so much when you get bit. by one of these fire ants is because they're injecting something in you that has a pH of 2.7. So again, let's look back on what it is that we did. You always have to have this Ka value and the initial concentration to be able to perform a question like this, where you just have the ice table and you're inputting X values and you're solving for X. Okay, so I took my initial concentration of formic acid, I created my ice table based off of this information, and then using my Ka value and my equilibrium expression found here, I'm able to find the two roots of X and determine which one is real in this situation. And that X value represents the concentration of hydronium in my final solution. And I could find the final concentration of the formic acid molecule before it's dissociated. I just have to 0.025 minus the X value. But what it's asking for is just the pH. And so I'm taking that X value, plugging into minus log of the concentration, and I get a pH of 2.7. And okay, that's it for that. I don't know how many of these questions that I gave you. They're all from the textbook. Again, you can find this, this worksheet on my website if you want to go through these examples, or you can just write it down.